Hi, and welcome to this section of the Chemistry Tutor. In this section, we're going to cover the very important topic of density and temperature, or temperature and density of a material, and also its basic definition, what it means in everyday life, and also what it means in terms of chemistry, because as you know, most of the challenge in doing well at chemistry and also of most courses is really getting a good understanding of the definitions. Once you get the bedrock down, then moving on into the more, what people think the complicated material is, more and more complicated material, gets easier and easier. So here we're going to talk about temperature first. Temperature is something you have everyday experience with. It's something that you kind of think you have an everyday association and understanding of, and in fact probably you do. What we're going to do here is put some real definitions to it. So let me ask you this. What do you think the concept of temperature is? I mean, we know that when we grab something quote-unquote hot, has a higher temperature, it burns our hands, right? We also know that if we go outside on a cold, snowy day or go into the freezer and grab something that feels very cold and an Arctic and just chilly, it has a lower temperature. All right, so both of those things actually in the extreme can burn you and hurt you. And why do you think that is? If you grab something, let's say something's very hot and it burns you, why do you think that that happens? Well, in a basic sense, temperature really is a measure of how much energy something has, a physical object has. The higher the temperature, the higher the energy content, we say, the kinetic energy of motion of the atoms and the molecules inside of that material. And so we say it has a higher temperature. So when you watch your thermometer go up to, 50 degrees, 70 degrees, 90 degrees, whatever, what we're really saying is that that material with a higher temperature has more energy. It means the molecules, the atoms, whatever's made up of, that material's made of, is literally vibrating more vigorously, really is what it means. So if you grab a hot object, that energy that's in the object is transmitted to your hand, and it ends up damaging your tissues because it's sending that energy of motion right into your hand, and it kind of, on a microscopic level, kind of rips it apart a little bit. That's why you get burned, right? So in a nutshell, that's what temperature is. Higher temperature means more internal energy of something. Lower temperature means lower energy of motion of the atoms of the molecules. So let's put that into words, and we'll talk about temperature scales here also. So the general concept of temperature, if I had to give it a definition that I would write on the board, it would be the measure of the internal energy of a substance. And don't be scared off by words like internal energy, because it sounds complicated, but you know from everyday experience what that means. When something has more energy and more energetic, it means it's moving more. That's what we mean here. So on a microscopic level, if you zoom into something with a higher temperature, the molecules or the atoms or whatever you choose to talk about to describe that object, they're literally moving more rapidly back and forth and kind of shaking in place. Because at the atomic level, everything is moving, kind of oscillating about some position. So when you have a colder object, maybe things are moving not quite so much. If you heat it up, put that energy into it, energy's got to go somewhere. It goes straight into the motion of those atoms and molecules, so they move a lot more. That's what we say more internal energy of something. Now, how do we measure it? We know we measure it with a thermometer, temperature scale. So let's talk about that. The main temperature scale that we use in chemistry, at least right now, is the Celsius scale. And it's really convenient. The Celsius scale is really convenient. Why is it convenient? Because 0 degrees Celsius, this is a degree symbol, 0 degrees Celsius is by definition assigned to be the freezing point, freezing point of water. The reason it's set up this way is because water is something that everybody has access to. So when they define the temperature scale, they just froze water and said, all right, at that temperature, which by the way, more or less, if water is pure, water's always going to freeze at the same temperature over and over again. We know this to be true. We call it 0 degrees Celsius. And also 100 degrees Celsius, we define by definition to be the boiling point. of water. The reason we define it this way is because it's just so convenient. If I go to another scientist, you got to imagine back in the 1500s, before the internet, before television and everything else, when you had scientists all over the world doing experiments, if someone said, hey, I want you to do this experiment at 0 degrees Celsius, well, that person knows exactly what that temperature is because they can calibrate it to just when water just begins to freeze right at that point. So everyone knows what that temperature is. Or if I say, hey, go ahead and do it at the boiling point of water, 100 degrees Celsius. Well, I can heat up some water. I know exactly what temperature that happens. And of course, nowadays we know the boiling point of water depends on your altitude. That's a total different lecture. But at sea level, the boiling point and the freezing point of water is always going to be exactly what we have it defined to be here. So what we're going to do is talk about this. Now, chemistry, we usually use Celsius temperature scale. So we're going to use Celsius in most of our chemistry calculations, at least early on here in the beginning, but there is another temperature scale that's used some. So I'm only going to present it here because it's useful for you to know about, and that's the Fahrenheit scale. The Fahrenheit scale. The most challenging part of the Fahrenheit temperature scale is learning how to spell it, okay? And it's, we use it sometimes here in the United States. It's used in some other parts of the world. It's not used very much in the sciences. I'm only giving it to you here just because, so you know how it relates to everything else. It's sometimes used. Sometimes if you look at an older chemistry book, you might find some tables that mention Fahrenheit in it. So I just want to let you know. Most of the time we're going to be using Celsius. So how does this compare? Well, in Fahrenheit scale, the freezing point of water is 32 degrees Fahrenheit, and that's the freezing point of water. And 212 Fahrenheit is the boiling point. So right away you can see that the Celsius scale is just so much nicer. I mean, just from a math point of view, 0 means freezing, 100 means boiling. I mean, I can wrap my brain around that. That makes sense. That's nice and neat because 0 and 100 are nice numbers. Having 32 for freezing doesn't make a whole lot of sense. Why 32? Well, there's history behind it. We could go into the history. The history doesn't even matter, though. That's just the end result. Same thing with the boiling point, 212. What's special about 212? Well, there's history behind why it was chosen the way it was chosen. The fact of the matter is, this is a much more convenient scale. All right, so yeah, we use Celsius most of the time. Fahrenheit is out there. So on your test, you may be asked to learn how to convert between these two guys. Now, most unit conversions in chemistry we talked about before, very easy to do. You have a conversion factor. We do the technique I showed you where you kind of drill the horizontal line, the vertical line, use your conversion factors and all that. It's great. That doesn't work for temperature. The temperature is the only thing that it doesn't work for, and the reason is because it's a long-winded reason. There's not a straight conversion factor between these two, and the real reason is because there's 100 units between 0 and 100 degrees Celsius here, but there's not 100 units between the freezing and the boiling point of water. So this scale is really set up completely differently than this scale, so it's not quite as easy to convert. But there is a simple equation that we can use to convert. The temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. So this is what you're going to use to convert between Fahrenheit and Celsius. If you know the temperature in Celsius, then you stick it in here, multiply, add 32, and you're going to get Fahrenheit. And just to prove that to you, let's talk about 0 degrees Celsius. If we put 0 Celsius in here, this term disappears. The freezing point of water is 32 degrees. Makes sense, right? If you put 100 in here and do the math, you'll find out that it comes to 212. So that's just something to think about. So let's go ahead and do a couple of quick problems to kind of illustrate how to deal with converting temperature, because it is different than doing the unit conversions of meters to kilometers and things like that. That's why I'm breaking this out kind of in its own section, just so you know how to do it. So if you want to convert, like we just said, 0 degrees Celsius to Fahrenheit, just to be complete, just to show you mathematically, the temperature Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. So you would just take the 1.8, drop 0 degrees Celsius in, plus 32. So the temperature in Fahrenheit is equal to, this multiplies to 0, So you're just left with 32 degrees Fahrenheit. So what it's telling you is 0 degrees Celsius is equal to 32 degrees Fahrenheit. Not too bad, because 0 is an easy number to deal with there. But what if you were doing 10 degrees Celsius and you wanted to convert to Fahrenheit? So again, you're going to use the same exact equation. Temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius, but that's given to us as 10 plus 32. All right, so the temperature is equal to, what's 1.8 times 10? What's 1.8 times 10? When you do this multiplication, this is 18, and you multiply it, you take the 18, you add 32, you're going to get 50 degrees Fahrenheit. And that's the answer. So 50 degrees Fahrenheit is equal to 10 degrees Celsius. You see how the scales look a little different? 50 degrees Fahrenheit, for those of us in the United States, that's a kind of a chilly temperature. It's not freezing, but it's kind of chilly outside. It's definitely cold. You need a jacket for 50 degrees. But in Celsius, that's 10 degrees. I mean, you can just see how cold temperatures are just set up a little bit differently. In other words, when you get a warm summer day in Celsius is something like 30 degrees Celsius. But a warm summer day in Fahrenheit is more like 90 degrees. That's a hot day, right? So the scales are just set up totally differently, and that's why we need to use this equation to convert between them. We'll do one more really quickly. Let's say we were going to go the other direction. Let's say we're going to take 75 degrees Fahrenheit, and we want to know what that is in Celsius. Well, you use exactly the same equation. Temperature in Fahrenheit is equal to 1.8 times temperature in Celsius plus 32. The only difference here is we don't know what this is, but we do know what the temperature in Fahrenheit is. So we just put it there. 75 is equal to 1.8 times Tc plus 32. So this is an algebra problem. How do you solve for Tc? First thing you do is got to get this 32 over here by itself by subtracting 32. So 75 minus this 32 is going to give you 43. And on the right-hand side, we still have the 1.8 times Tc. We haven't done anything with that. All we did was subtract 32 from both sides. So it disappears over here and it comes over here. Now to find the temperature in Celsius, we just divide both sides by 1.8. So it disappears on the right because they divide out, giving us 1. On the left, 43 divided by 1.8. So let's just do it like this. 43 divided by 1.8, which is equal to 24, or I should say 23.8, which for the purposes of what we're doing here, 24 degrees Celsius is what we're converting to. So you see, when you're going from one temperature to the other, it doesn't matter which direction you're going. You use exactly the same equation. It just depends on where you put your known quantity. If you know Celsius, you stick it here, you easily calculate TF. If you know the Fahrenheit, you just put it in there, subtract the 32, divide by the 1.8 to isolate, the temperature in Celsius that you want, get 24 degrees Celsius in this case. Now that we've gotten some practice with talking about Fahrenheit and Celsius and converting between the two, I want to wrap up the section by talking a little bit more about the Kelvin scale. The Kelvin scale is used also in chemistry, but we use it a little bit more, a little bit later in the course. But it's very easy for you to understand what it really means. Basically, when you have 0 degrees Kelvin, it means that all of the atomic motion that's kind of present inside of every object you've ever touched goes to 0. It means that as we increase the temperature of something, the atoms and the molecules, they're vibrating around, and the higher the temperature, the more and more they're vibrating. The lower the temperature, the less and less they're vibrating. Well, theoretically, if you decrease the temperature enough, all the way down to what we call absolute 0, which is 0 Kelvin, that means that the atoms don't move at all. It means that they vibrate less and less and less and less. Eventually, at 0 Kelvin, they stop. Now, nothing in nature actually exists at 0 degrees Kelvin, but some things get pretty darn close. For instance, helium, regular old helium that you put in a balloon. If you cool it down enough, it'll turn to a liquid, just like anything will turn to a liquid if you chill it enough. Liquid helium actually exists at around 4 degrees Kelvin, which is extremely cold. Liquid hydrogen behaves at very, very cold temperatures also. But even if you go out into the depths of space and sample the temperature deep in the universe, you shouldn't actually get all the way down to absolute 0. It's kind of a theoretical thing. Whenever the temperature decreases to the point where nothing is moving anymore, That's what we call 0 degrees Kelvin. We're going to teach you how to convert back and forth to 0 Kelvin later on when we get to the point where we're actually going to use it in the class. But for now, I just wanted to give you an idea of what it is so you're not worried about it, because there's really nothing at all to be worried about Kelvin scale. For the most part in chemistry, we'll be dealing with Celsius. So we talked extensively about Celsius in this section. 0 Celsius is freezing point of water. Boiling point of water is 100 Celsius. So it's a nice temperature scale. 0 and 100 are nice little anchor points that we have based on everyday experience. When we go to Fahrenheit, which is used a lot in the United States, unfortunately Fahrenheit is it's used a lot, but it's not very good for science because it's a kind of an arbitrary scale. 32 degrees Fahrenheit is freezing point of water. 212 degrees Fahrenheit is the boiling point of water. Those numbers, they're not even round numbers. They're not even nice numbers. There's a lot of history behind why they're picked the way that they're picked, but for science, we're not going to use Fahrenheit too much, but we did learn how to convert back and forth because that's a useful skill for you. So that concludes this section. Everything we learned here we're going to be using as we go on throughout the course, primarily because, and this is a new piece of information for you, the chemical reactions that we're going to study, most chemical reactions in nature are dependent upon temperature in general. All right, so you may or may not have known this, but if you actually heat up a chemical reaction, if you have a vessel and you're doing a chemical reaction in it, it's bubbling and it's doing all these things, if you heat it up in general, the reaction will proceed much more rapidly. It'll go from start to finish much more quickly because you're adding energy to it, causing everything to mix more and agitate, so it's going to go faster. If you put something in the freezer and chill it down, in general, the chemical reaction will proceed much more slowly. So all of these reactions that we're going to talk about later in the course, almost all of them are going to be dependent upon temperature in some way, shape, or form. So that's why we introduced temperature here, and we're going to be coming back to it as we go throughout the course, and using these concepts as we go forward. I'm Jason. I hope you learned something in this section. Make sure you understand temperature. We're going to use it a lot throughout chemistry. Not a hard topic, but it is something that you do need to learn how to do.